My name is Todd Whipke. I'm the chair of the Emeriti group here at UCSC that sponsors the Emeriti lectures. We have two lectures, one in the fall, one in the spring. This is the 12th of the series. It was founded in 2003 by Joe Bennett, Professor Emeritus of Chemistry, and in his words, to feature the research of our retired faculty and to make a substantial contribution to the intellectual environment of the campus. We would like to thank the Chancellor's Office, who financially sponsors the talk and the goodies afterwards. And I would particularly like to thank Kristen Palma and Rebecca Alvarez from the Special Events organization, too, who helped organize tonight's event. The lecture is being recorded, so turn off your cell phone. I'll give a how-to here. It's always embarrassing if mine goes off. And it's not just for the noise, it also interferes with wireless mics. This will be available in a podcast on YouTube and also at podcast.ucsc.edu if you have friends that missed it. Tonight's Emeriti lecture is going to be given by Ralph Abraham, Professor Emeritus of Mathematics, whose research interests are dynamical systems theory and its applications. A little bit of background: he received his PhD in mathematics from the University of Michigan in 1960. He taught at Berkeley, Columbia, Princeton, and then moved to Santa Cruz in 1968. He's held visiting positions at a lot of interesting places: Amsterdam, Paris, Warwick, Barcelona, Basel, and Florence. Author of more than 12 books, including 7 currently in print, in translations into 9 different languages. With the modern electronic age, 4 of his books are available as e-books: Chaos and Discrete Dynamical Systems from Amazon, Foundations of Mechanics, which is free from Caltech library, so you can run out and download it to your iPod or whatever device. Chaos, Gaia, and Eros from Amazon, and Transversal Manifolds and Flows, also from Amazon. As you can tell, he's into chaos theory. He's a consultant in its applications to a variety of fields, including medical physiology, ecology, mathematical economics, psychotherapy, among others. He's also an active editor for the technical journals World Futures and International Journal of Bifurcations and Chaos. He's always been interested in graphics, and I think tonight's lecture will be a visual treat for that reason. He founded the Visual Mathematics Project at UCSC in 1975, when I came to this campus the same year. It's also known now as the Visual Math Institute. He retired in 1994, and I'll do the math for you. That's 15 years ago. And on his website, he lists that he has 2 most recent projects that are near completion, and he tells me that they actually are now at the publisher, a book called Demystifying the Akasha, Consciousness and the Quantum Vacuum, joint with Sisir Roy from the Indian Statistical Institute at Kolkata, finished in June this year. And another project that is also a book at the publisher called Bolts from the Blue. That's the topic of tonight's lecture, but he indicates that tonight's lecture is actually newer than the book and has additional information. So the title is Bolts from the Blue, Startling Episodes from the Coevolution of Mathematics and Arts. Following the lecture, we'll have questions and refreshments. So please welcome Professor Emeritus Ralph Abraham.
My goodness, this is like Thanksgiving dinner. It's such a privilege to stand on this stage in a splendid recital hall and look out over a gathering of almost all the friends and colleagues I've known in 40 years in Santa Cruz. And the occasion of such a spectacular audience gives me license to do a risky experiment in this lecture. And what I want to do is tell 5 exemplary bolts from the blue. And that's too many. So I've got to speed along here. And if you have questions, please make note and remember, because there'll be so many changes of theme by the time we get to the Q&A section, you might forget your question. So I'm very grateful for this opportunity, and I especially want to thank people who assisted me in the content of this talk. And first and most importantly, William Irwin Thompson, who is a cultural historian, who has been my partner for 25 years in a project of the application of chaos theory to world cultural history. So if I only wanted to tell you what is a bolt from the blue, which, by the way, means for me a significant contribution to the history of mathematics by an artist. Well, it sounds like a category for an Emmy Award. And the nominees are, so there are 5 nominees, and I'm going to introduce them one at a time, and when I'm done, we can take a vote on who is the biggest bolt of all. But the reason I'm not satisfied to give one example of a bolt from the blue and just list a few others for later reading is that I have an additional agenda, and that is a theory of world cultural history called the mathematical mentalities. And here is the idea of it in a nutshell. First of all, we look at culture or cultural history as a complex dynamical system. That means something like a neural net. That means that there are nodes or neurons, maybe zillions of them, and they're interconnected by links that carry information. And as culture evolves, and the evolution of culture is some kind of basic question that we never tire of studying. As the culture evolves, the nodes or neurons may become more numerous, the links become more numerous, there may be emergent behavior or major cultural transformations, and the links may also repattern themselves in a kind of plasticity, like a neural net, which we might call learning. And as in the case with the psychological development, there are stages, like stages of Piaget, where there are major transformations or sudden quantum leaps, changes of strategy, of style, and then long, flat plateaus. So this idea, culture as a complex dynamical system, we've been studying for 25 years. It's not our idea. That this emerged, as far as I know, with the cybernetic group, multidisciplinary group meeting in the so-called Macy conferences after World War II that gave rise to, well, what we called cybernetics for a while. Maybe younger people have not heard of it. Furthermore, there was an idea coming from the catastrophe theory branch of mathematics in the 1970s, an idea that a mathematical concept which will come into the collective conscious, the noosphere, the global brain, as soon as the wiring diagram of that global brain is sufficiently complex to actually represent that idea. Nobody has to try and wait a long time. As soon as, according to this idea, as soon as the opportunity was there, somebody, somewhere, maybe an artist or intellectual or somebody in a mental hospital will get that idea and run with it. So applying this point of view to the history of mathematics, we see there are basically at present 5 stages, which I identify with the letters RGADX, and as a mnemonic, I pronounce that argadics. So each of these mathematical modes then becomes a center of attraction for recruiting other aspects, other neurons, nodes of the global brain, so that the whole culture is reorganized according to the new mathematical idea. That is what we call a mathematical mentality. It's the new mathematical idea triggers a global cultural transformation. And we could see that somehow in looking at the detritus, the archaeological artifacts, and so on. For example, the advent of the geometric mentality is evidenced by the great pyramids of the Giza Plateau, or the megalithic monuments of Britain like Avebury and Callanish. So these 5 mentalities, argadics, are for arithmetic, which I don't use A because I need A for algebra, G for geometry, A for algebra, D for dynamics. That means the early dynamics of Galileo and Kepler, Newton, and so on. And finally, the chaotic mentality, which we are seeing in a process of emergence right now. Now, one way of displaying the geography in space-time of such cultural events is in a so-called histomap. This histomap, let's see. Here's my pointer. Here it starts at 2.5 MYA, million years ago, okay? And then we have the early hominids. This diagram from Colin Renfrew, very recent book called Prehistory. He is the leading prehistorian of Britain. So basically an archaeologist, and that means that he digs down from the surface. So we have the time axis here. It starts at 0, that's now. And then as you dig down deeper and deeper into the soil, you're going deeper into past time. And so here we have the evolution and dispersion of hominids from Africa, North Africa, and the Middle East and Europe. And below this lake here, we have Neanderthals, and above Homo sapiens. So on this kind of histomap or space-time diagram, I want to locate then the origin points of our 5 mathematical mentalities, or at least the 5 exemplary cases, the nominees for this year's Best Bolt award. So that red rectangle, then I'll expand that, blow it up. And here we have on the vertical axis on the left, 100,000 years ago up to the surface and the present. And so we can see clearly the boundary between the Neanderthals and Homo sapiens, and there that R represents our nominee for the R, or arithmetic mentality category. And then where are the other four? We have to blow up this rectangle, looking then at 10,000 years of prehistory and history. We see the G, the geometric, emerging about 5,000 years ago. That's, in other words, around 3,000 BC or so. And then algebraic, dynamic, and chaotic are more recent. And our exemplary bolts, our nominees then, are the canon of LaPook, the Bethels of Scotland, and so on. I'm going to introduce them one at a time. Here is the so-called Venus of LaPook. This is a sculpture 25,000 years old, approximately 6 inches high, that was dug up in a cave in the south of France in the foothills of the Pyrenees. It is typical of a large number of similar figurines called the Venus figurines that dispersed all over Eurasia, and 3 main groups: the Western group, the south of France, and the middle group north of the Alps, and then this East European group. So somehow these are identified with mother goddess religion, which is very long lasting around the globe. And so our particular Venus figurine, the Venus of LaPook, comes from down here. Now this was a unbelievable suggestion from my pal William Irwin Thompson. He bought a replica of this statue in a museum store in Paris and sent it to me and said, "You measure the typical lines on this figurine. I think that it's a canon, that is to say, a musical scale." Thought that was ridiculous, and I put this statue away. I didn't touch it for a long time. But here we have a book from a musicological text on musical arithmetic, and it's a nice illustration. Here we have a flute, and the holes, of course, define the tones of the ascending scale. And here are the measurements, and rescaled into some kind of normal units called the Davidian scale. And these are the measurements in length units of the distance between the holes in the flute that correspond to a particular mode of the many, many musical modes, one of the 10 Greek modes called the Dorian mode. This you can play on your piano using the white keys only if you start with the tonic on E. It's a weird mode, and with this as a reference, then I finally got around to measuring the figurine, the Venus of LaPook, with these results. Here we have the measurement rescaled to go from 72 to 144. The measurements of the most obvious lines that I could draw using a computer graphic program over an archaeological photograph of the actual figurine. I just, drew lines that seemed evident there at the knees, the crotch, the bottom of the butt, the breast, and the chin, and the top of the head. And I just measured them in millimeters and rescaled and got these numbers. Amazingly, when I compared with the musical arithmetic text, I see that they're almost exactly the same, only this one, the seventh note, is a little bit flat. The accuracy phenomenal. So William Irwin Thompson's intuition was correct, and it looks as if this Venus of LaPook is a guide for musicians who would construct a flute or maybe a lute and put the frets on the fingerboard in the proper places to play the scale that is agreed to be the pleasant scale for that particular culture of 25,000 years ago. Now that seems unlikely. Could these people so long ago be so sophisticated musically and arithmetically to carry out this arithmetic? So turning the figurine over, we look at the backside, and indeed it appears that there is a bridge and 7 or so strings are gathered together at a nut at the bottom. So it suggests that they did have stringed instruments. Now, you still might say, I don't believe it's a musical reference. I think the numbers are an accident, and people at that time couldn't possibly be so sophisticated to make this musical scale accurately. And this is not the backside, the bottom of a lute. What we're looking at here is a grass skirt or something like that. However, recent discoveries in archaeology have provided us with an actual flute. The earliest known flute at present, 35,000 years old, is made from the leg bone of a red-crowned crane. And here we don't see, there's not enough holes to test out the scale and see what it is, but here's another one. The oldest known at present time, the oldest known playable flute is 9,000 years old, and there is a tune played on this flute which for a while was downloadable from Nature magazine website. So that's my nominee in the category of arithmetic, or the R mathematical mentality. Let's go on to the next one now. I'll do this a little faster. The Bethels of Scotland are stones that have been carved in three-dimensional geometrical shapes. They're quite profuse over Scotland. More than 400 have been discovered, and they're all gathered in a museum in Scotland. And to understand what I want to say about the Bethels of Scotland, we need to know about Euclid's Elements. Now, Euclid's Elements is the most important mathematical textbook of all time, still may be used somewhere as a textbook, but until recently, everyone studied. Even when I was in middle school, we studied geometry from Euclid's Elements. So published in 300 BC in 13 volumes. And every mathematician of note until recent times had learned from this book. It introduces the logical method with definitions, theorems, proofs, axioms, and so on, very carefully done. Studying this book, which I have actually translated from English into pictures, you find of the 13 books that there are 9 books devoted to geometry, and the remainder are devoted to number theory. The books devoted to geometry contain 600 or so theorems and proofs, but only a few of them are constructions. They tell you how to actually do something, for example, bisect a line segment. using a compass and straight edge alone. If you go through all these books, you come at the end in book 13 with these 5 so-called Platonic solids, the cube, the pyramid, tetrahedron, icosahedron, dodecahedron. These basic shapes are the goal of the 13 volumes, that you could actually construct these out of cardboard using nothing but a compass and a ruler. If you follow the instructions, it's a very, very long construction, and after these constructions, Euclid proves that there are only 5 of these so-called regular solids. That came together in Plato's Academy in 300 BCE. Kepler was fascinated by the 5 Platonic solids, and he tried to show how the dimensions of our solar system were determined from these solids by God, who considered them divine, according to Kepler. And he followed then in the tradition of Plato, who in the Timaeus had constructed the whole universe out of these 5 figures. So, looking through the Bethels of Scotland, we find that all 5 of the Platonic solids are represented there by these sculptures. These are carved in diorite, which is a very hard stone. So with great difficulty, why we don't know, these shapes were saved up for posterity in Callanish, which is up here is England, Wales, Ireland, North Ireland, Scotland, and way up here on these little islands in the northwest of Scotland called the Outer Hebrides. There in the red marks Callanish, which contains a megalithic monument of standing stones like this. And this is in the time of the megalithic cultures. So they not only made these huge stones, but also small ones. So our next nominee, this, I have to really discipline myself not to go on for an hour about the Alhambra, but this is something that I had not even heard of really until 2 years ago or so, when I was invited on a school trip of the Ross School, which is a private school in East Hampton, Long Island, where I have been consulting on the curriculum for a long time. They took me along on a school trip to the south of Spain, and the idea there was to understand how it was in medieval times that 3 cultures could live together in peace, the Jews, the Christians, and the Muslims. And so we visited all the mosques, the cathedrals, and the synagogues of this area with professional guides. And the last place we went is a palace called the Alhambra, that means the Red Fort, or the Red Palace. There it is on the top of the hill in Granada. Here's a little chronology of the beginning and the end of the Moorish civilization. So in 711, a Muslim invasion of Spain from the south, from North Africa. They quickly conquered the whole of Spain. They got stopped up in the north somewhere, and little by little, the Christians then began pushing back in the so-called Reconquest, and by 1492, the Reconquest had pushed the Moors out of Spain. That's the year Columbus sailed the ocean blue. So as the capital of the Moorish culture was pushed further and further to the south, the last place that it rested before getting the boot altogether was Granada, and there this palace, the Alhambra, was built. And it is covered with the most incredible patterns that are so-called wallpaper patterns. There are tiles in every room, and there are a lot of them, and each wall has a pattern that is unique and astonishing with with colors, the precision, the geometry, and so on. Here are just a few of the patterns. Now, mathematicians had eventually studied this kind of thing, and understanding these patterns requires group theory, groups of transformations that are used to define symmetries. And the idea of a group in modern mathematics came from these studies. Nowadays, one says that the group concept is one of the most important ideas in the whole of mathematics. So we're looking at, certainly from looking backwards from the perspective of now, this is algebra, but this algebra was performed by craftspeople in tiles, in glazed stone. It became known about a century ago in the field of crystallography. The crystallographer in Russia, Fedorov, proved that these wallpaper patterns are of exactly 17 distinct types, and no more and no less. Yes? Sorry, thank you. So there are 17 types of patterns. They are defined by the so-called crystallographic groups, and these are generated by rigid motions in 2 dimensions. That means the translations, rotations, reflections, and so on. No time for the details there. All that I want to share with you now is that in the Alhambra, recently, all 17 types have been found. And that means somehow that the craftspeople in these tiles had figured out Fedorov's theorem some hundreds of years before Fedorov. Now, if we had time, I would try to explain a little bit easily about the 17 groups by specializing to a one-dimensional case. Of the 17 wallpaper pattern types, there are 7 that are frieze pattern types and 10 that are truly two-dimensional. The frieze is this one-dimensional row in the middle here of these 2 patterns, and they have symmetries along the horizontal dimension only. So there's 7 kind of groups there, and in Coxeter's book on geometry, you find them explained in a very simple way in terms of these patterns. So where you see L, 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 you're supposed to imagine L, 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 L being repeated indefinitely to the right, also indefinitely to the left, and that's an infinite pattern, and it shares a symmetry generated by a single translation. That means that whatever is that distance between 2 neighboring L's, you move the entire strip or frieze that distance to the right or to the left to generate this pattern. And there are all the types, 7 types classified by Fedorov's theorem. Now, the 7 frieze groups are simpler than the 17 wallpaper groups, and if we look through archaeology as much as we can to identify examples of these frieze groups, we find they all originate in Çatalhöyük, which is a pre-pottery Neolithic village in Anatolia. So 10,000 years ago, the beginning of the group concept in algebra in this particular civilization in Western Turkey. And here's a frieze that goes around a dish. Frequently, you see them in pottery in cylinders going around the outside and so on. And those examples of frieze patterns and wallpaper patterns in Çatalhöyük, it is known they're wall paintings that were copied from carpets. So the fiber technology 10,000 years ago was adequate to weave these very intricate mathematical patterns in carpets to keep people out of the mud. Okay, this is the fourth of 5 nominees for the biggest Bolt Prize. And this one I call Kepler's Music of the Spheres. We saw this slide before, which is the frontispiece of Kepler's first book, Mysterium Cosmographicum, published in 1595, the same time that Galileo was doing his first experiments with rolling baseballs down a gutter. And if we look at the top view of this as a fantasy sculpture, Kepler wanted this object to be created by a sculptor. That never happened. But if we look at the top view, the idea of it is this. Here we have the solar system seen from far above, so that this purple ring represents the orbit of Saturn, which is an ellipse. And the ellipse is to be imagined grazing the outside of this ring at one point and the inside of the ring later on. So the width of that annulus represents the eccentricity of the orbit of Saturn. And here on the right we have the inner planets, Mercury, Venus, Earth, Mars. Mars, the red planet, that's red, and that red annulus is here in the larger picture. So on the right we have a blow up. These are just some details from Kepler's fantasy sculpture. Now, I want to describe this as a play with a cast of 4 characters, and these are the lifelines of the 4 characters. First, there's Vincenzo, who's the father of Galileo. Now, Vincenzo was a noted musician in his time, a player of the lute, and also a music theorist who had studied with Zarlino, famous music theorist of the Italian Renaissance, and disagreed with Zarlino about how the scale was to be defined in terms of numbers. Vincenzo felt that when people sing together and make harmony, like barbershop singing, that they should be able to make free with the intervals defining the harmony, so that with a little bit of detuning of the interval, dissonance would be created, and that dissonance would be under control of the individual singer and could warp the note as they do in Indian vocals in order to control that dissonance. So Zarlino felt that people should only sing in harmony. Vincenzo disagreed, and in doing so, he founded experimental psychology by doing experiments where he asked people to tell if this or that degree of dissonance was pleasant or not. So instead of going by the gospel of Pythagoras and so on, Vincenzo wanted to do experiments, and it is thought by some Galileo historians that Galileo's idea, founding modern science on this experimental idea, was actually learned from his father, who drafted Galileo as a research assistant in the kitchen where the experiments were done. Next, we have Kepler's mother. Now, Galileo and Kepler were contemporaries, and so the father and mother were sort of contemporaries, as you can see by these lifelines on the left. Caterina is remembered in history. Whole books are written about her because she was accused of witchcraft, and many people try to explain that away as due to the prejudice of the time, which it is true that in the town in which Caterina lived, almost half of the women were accused of witchcraft. Nevertheless, in her case, I would say in retrospect, she was accused of witchcraft because she was actually a witch. And her witchiness was manifest in what we would call naturopathic medicine. That is to say, she treated people's illnesses with herbs and flower cures. Then there's Galileo, the third bar on the left, and the contemporary Kepler, just a few years younger. So this story has to do with contribution to mathematics by the artist Vincenzo, and that contribution is manifest finally in Kepler's work. Kepler got somehow an idea from Vincenzo. This is how it happens. First, Vincenzo works with Zarlino. About the same time Galileo is born. Just shortly afterwards, Galileo is a little boy. Vincenzo is beginning his study of dissonance as an artistic technique. 20 years later, he dies. At the same time, publishes his main book, Dialogue on Ancient and Modern Music in Italian. And at about the same time, Galileo goes to Padua to begin his career as a professional mathematician and dynamicist. So these events involve only Vincenzo and Galileo here, and are nested like that. About Vincenzo, his historian, Palisca, says Galilei, so that's Vincenzo, was the first modern music theorist to espouse this non-mathematical approach to the construction of a musical scale that made the equal temperament of the diatonic octave possible. In other words, music today, played polyphonically with different instruments, the organ, the clarinet, and so on, has an approximate harmony that's made possible by the agreement to use the equal tempered scale. So that's one of Vincenzo's contributions. So here's a little chronology of Kepler. This is mainly what I want to tell you. First of all, he publishes his first book, The Mysterium Cosmographica. Then he publishes the second book after moving to Prague, called Astronomia Nova. And here, Kepler is famous for the 3 laws of planetary motion. 2 of them, published in Astronomia Nova, depend upon his efforts to prove that the Platonic solids actually determine the dimensions of the solar system. Okay, a few years later, his mother is accused of witchcraft, and she begins then a trial that lasts 6 years, and in the end, she is released and dies. But shortly after her accusation, the trial begins. Kepler has to go from Linz, where he's living, to the south of Germany, where the trial is taking place. He takes a carriage, a long carriage ride, takes several days. In that carriage, he reads Vincenzo's book on the dialogue of ancient and modern music. Inherits the idea of controlled dissonance, realizes that could explain the old myth of the music of the spheres, and he produced a formula to determine the pitch of the song that would be sung by each and every one of the 6 planets according to its angular velocity seen from the sun. And 2 years later, he publishes Harmonica Mundi, his final important book, in which he publishes the 3rd of the 3 laws of planetary motion and his theory of the music of the spheres. So Vincenzo suggests to Kepler how planets should sing with controlled dissonance, and out of that comes the 3rd of the three laws, which has to do with the relationship between the speed of the planet and its distance from the sun. Kepler imagined that people, he's religious. I mean, people were religious at that time in a way that I think we can't even imagine. Nobody's really that religious now. Kepler, superb mathematician, intellectual, free-thinking, going his own way. He thought that the biblical story of creation was true verbatim. So, according to Kepler, God would not create such a beautiful universe, that the solar system with these perfect dimensions satisfying the first, second, and third laws of planetary motion, unless there were some people, some beings somewhere to appreciate that beauty. So Kepler insisted that there were beings living on the sun. And the beings living on the sun are the beings who would hear the celestial music. That would just be part of the beauty of the solar system. So you imagine that you're sitting on the surface of the sun, probably as a disembodied spirit so you won't burn. And where you're sitting, it's nighttime and you're having dinner with a glass of wine and looking out through the window, you can see the planets as they pass by. So here they are, all lined up. That's Mercury at the top, and then going down, Venus, Earth, Mars, see Mars, the little red planet, and then Jupiter and Saturn. Now, their sizes are more, differ more than it appears here, but this is how they would actually appear if you look through the window from the surface of the sun, because the larger ones are farther away and their angular aperture is known. And so in a little flash animation, I created this picture, and you imagine now I'm going to start the animation, and Mercury at the top goes real fast, so it'll keep flashing by the window, while Saturn at the bottom moves very slowly. Well, the animation doesn't start, but you can hear the music of the spheres as each of these planets sings the song according to the rules that Kepler published in his third book. Oh, there they go. Here they don't go. See, the planets are winging by, singing. You only see the planet when it goes past the window, but you hear the song it's singing all the time. And this music was created by my partner, Pablo Viatti, and we performed this in San Francisco at the San Francisco Art Institute. And there we had a full surround system so that you heard the planets actually going around you as you sat on the surface of the sun. Okay, the fifth and final nominee for the Best Bolt Award is a painter called Franciszek Kupka. And he was in that modern painting group in Paris that did Cubism and so on, you know, at the turn of the 20th century. And in the year 1910, about, Kupka, living in a garret in Paris, burned all his paintings. He had some kind of epiphany in the night, or maybe a mental disorder, and he burned all his paintings, and he considered all this Cubist stuff trash, and he started over with a completely new idea. To appreciate it, first we have to know about Poincaré invented a mathematical object called a homoclinic tangle that he felt was too difficult to describe or draw. So this in 1889, of course, preceded computers, and one could not examine the mathematical object that he was studying in the detail to actually draw this figure. But later, Yoshi Ueda in Kyoto as a graduate student saw the first chaotic attractor, and in it he drew from the measurements of an analog computer. He created this drawing of what Poincaré had tried to describe some generation before. And this became really seen in mathematics for the first time when analog computers made it possible to see that, and this is more or less the alpha moment for chaos theory. He is known as the first pioneer of chaos theory. Okay, in 1912, Kupka painted this, almost exactly the same. He had a series of these called the Amorpha series in the span of a few years. And essentially, he foresaw the chaos theory that Mandelbrot created with computer graphics in 1977. So that's the end of the nominations then. And with the 5 cases, I've tried to give not only the idea of a bolt from the blue, for example, who carved the Venus of LaPook was some kind of musician or musical theorist, who carved the Bethels of Scotland was some kind of sculptor, I suppose, fascinated by the abstract shapes to such extent to invest months and months of carving in this hard stone, and so on. Each is an example of a bolt from the blue in the sense of a significant contribution to the history of mathematics made by an artist. So why 5 of them? Well, each one epitomizes somehow the mathematical mentality, argatics. So our arithmetic, we have musical arithmetic. That's the measurements of the frets on a guitar or sitar, having to do with ratios of small integers, so special rational numbers. And so on. So the geometric mentality, the algebraic, we have the group idea seen by artists who were essentially weaving the first carpets 10,000 years ago. So those are the individual then nominees for the Bolt Prize. But if we look at them in sequence, then we see that occasionally there is a major social transformation. After the onset of G, the geometric mentality, the arithmetic mentality, R, continues. We then have 2 different cognitive styles coexisting. This is the beginning of the multiple intelligence theory of Howard Gardner. After the algebraic mentality comes along, we then have 3. Furthermore, the interval of time between these major cultural transformations is decreasing all the time. So we have D, that's the Galilean dynamics, 1600. Then we have X, or the Greek letter chi, the first letter of the word chaos, spelled in Greek. 1900 or 1960 or something. It has decreased from thousands of years to hundreds of years. And so here I've got argatics with Y. Y is the next one. So when is the next one due, and what will it be? This is kind of why we read history and prehistory, is to get an idea of the trajectory of the whole enchilada, world cultural history on planet Earth, in order to be able to foresee vaguely a little bit what's coming in the future, and therefore perhaps get ready, which readiness might or might not be the basis of survival or sustainability. So that's what I wanted to say. There are some references. I'll post these on my website somewhere, which you see there, ralph-abraham.org. And under articles or books, you will find somewhere the notes of this lecture if you wish to do more reading.
Thank you, Ralph. Do we have any questions? Start in the front here.
Thank you very much. You make a convincing case that there's a lot of parallels between these bolts and particular mathematical work, but I didn't see a whole lot about the causal relationship between these bolts and particular work by particular mathematicians. Could you talk more about that causal relationship?
Yes, thank you. You did indeed spot an important omission. Now, there is no doubt about the five mentalities, because if you look at any book on the history of mathematics, there you will see the chapters. But the idea that a new mathematical idea could be the center of organization of a whole cultural style, that is total speculation. And we think if you look in the details of history, you find evidence for this, and you may look and find, or you may look and not find and not believe in this connection. Either way, we have no idea what is the cause. Maybe I present it this way because I hate to say I'm this or that, because I try to study different things, but there's no doubt about it. I am a mathematician. I see math as being the most important subject in our culture. And there's never been a high culture without mathematics. And if we lose our mathematics, which in fact is happening, then our survival is doomed. It's just a personal feeling. I'm coming from there. On the other hand, William Irwin Thompson is a cultural historian who describes himself as being math-phobic. He has math anxiety. He has the math avoidance reflex. Nevertheless, I feel he has an enormous intuitive grasp of complex dynamical systems theory, chaos theory, complexity, and the like. He has written several books trying to make a case, not causal, but just for a case for the step-by-step recruitment of various aspects of culture by the new mathematical idea in a series of books. So I recommend you maybe Google him up. Okay, he has a blog, a weekly blog, the latest one. He is very brilliant at applying the basic ideas of complex dynamics to current events. So that's the best I can do for an answer.
Ralph, is there any reason why it starts only in Europe? You center on Europe?
No. I presented exemplary cases. I didn't talk so much about the origin. In the case of group theory, the wallpaper groups, beginning with the frieze groups, beginning with the first friezes, we saw them in Çatalhöyük. I just didn't put, I could have put a PA, pre-algebraic, that in Çatalhöyük, it's in Anatolia, eastern Turkey, close to North Iraq, where those Kurds live. And so that would be in the middle of my three columns. So in fact, there is a diffusion. If you could follow any one of these ideas back, you would find an endless trail that goes all the way back to Africa.
Let me start by reading a little quotation from Albert Einstein concerning mathematics and reality. He says, as far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. The other quotation I want to start, because I think it's related to your lecture, is of course from Wigner, who spoke about the unreasonable effectiveness of mathematics, asking essentially, is it a miracle that mathematics represents reality? Now, I think your lecture gives some hints as to why mathematics and reality are connected, because mathematics, if you view it as starting from applications, it sees the regularities, the symmetries in nature, the symmetries in carpets and so forth, and it builds on that. But I wonder if you could take up these challenges of Wigner and Einstein and give us some insight in your answer to the question, why is mathematics really so effective, especially when it becomes more and more abstract, and yet it continues to dominate all our science?
Yes, well, I'm very sorry that you asked me such a difficult question when I'm standing here and everybody is watching while I try to deal with it. Now, about the unreasonable effectiveness of mathematics in the sciences, I personally tend to the miracle idea. That is to say, I'm kind of a Platonist, but there are, let's face it, two perspectives here, and no one can decide what is right. I have a friend, Rupert Sheldrake. We have recorded books of conversations called Trialogues with Terence McKenna, and this question is a frequently recurring one in our conversations because he has the opposite idea that I do. Rupert Sheldrake is an evolutionist. He thinks the mathematical sphere of Plato is in coevolution with human thought, whereas I tend to more the Platonic view that mathematics just is somewhere. And when the noosphere, the neural network of human consciousness, achieves a sufficient complexity to engulf an idea, it will pop down from the Pleiades or whatever into consciousness. Nobody can, I mean, this is just religion, basically. Nobody can say what is right here. I believe that the reason for Wigner writing as he did has to do with this very, very arcane and abstract branch of mathematics having to do with the representation of Lie groups and Lie algebras, in which certain diagrams occurred in such an abstract context that nobody could believe that they actually were found in the configurations of elementary particles after the fact by high-energy physicists. That is the kind of case that inclines me to be a Platonist and inclines Wigner to write as he did that question. I think that mathematics is somehow divine. The little that we know of it this is where the confusion arises between me and Sheldrake's idea of evolution. Of all the objects and ideas in the mathematical sphere, only those that we are ready for can emerge into collective consciousness. And that means that we have been prepared. Our neural net, as it were, collectively has evolved according to our experience of reality, including with lasers and telescopes in orbit and so on, high-energy apparatus. So it always appears as if the mathematics we know is very close to reality or nature as we understand it. Is this epistemology versus ontology or something? We're getting into difficult waters where philosophers are happy to read and write and think and tread, and I'm not. I'm a practical guy. And for me, I learned mathematics that people have discovered in the past, and I'm working on the frontier. In fact, I will take this opportunity to make a speculation about the major bifurcation Y, the next major cultural shift, the next mathematical discovery coming along. And that has to do with agent-based modeling, which is a technique of model building emerging in the computer sciences for which there is as yet no mathematics. Nevertheless, in the behavior of models that we build using this agent-based modeling software, we see the behavior which looks very familiar from our study of chaos in complex dynamical systems. So I think that what has emerged as a new discovery in engineering, let us say, is going to precipitate a new mathematics that will give us a new mentality which will be the basis for our solving huge problems such as global climate warming or cooling, whatever it is, and nuclear proliferation and starvation, the destruction of the blah, 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 all that. We need more intelligence of complex systems in order to do that. We need a miracle. We need why.
Any other questions? Easier ones.
Kind of along the same lines of, you're thinking that mathematics is the basis. I'm just thinking about fractal geometry, and even though it's kind of a new concept, it's been with us for millennia. Fractal geometry just didn't appear. It's been with us, forever, and we were aware of it subconsciously. So perhaps that's a good argument that mathematics is the basis of all this.
Well, thank you. It's not a question, right? Well, I think fractal geometry is a really interesting example of this epistemology idea that the universe is how we perceive it, you see. Now, Galileo is the one who wrote, he was another one of these religious crackpots. He said that the universe is the Bible. The universe is God's book, and it's written to be enjoyed. It's beautiful, it's miraculous. But the problem is, God's book, nature, is written in the language of mathematics. Therefore, if you want to be devout and you want to read the book, you've got to learn the language of mathematics, by which I mean, he said, lines, triangles, and figures like that. So he didn't mention fractals, you see. And so until recently, nobody saw the forest litter, the leaves and the trees, the clouds in the sky, the mountain horizon, all these things are fractals. Nobody noticed because we didn't have the mathematics, and this comes back to why mathematics come first. Since mathematics is our most exquisite description of nature, when there's an advance in mathematics, we see more of nature, and when we acquired fractal geometry in 1972 or so, we began to see a whole lot of nature, maybe almost all of it, that we had never seen before. We couldn't grok it because we didn't have the mathematics, you see? Nice question.
Any other questions? Here?
That you used music as an example for mathematics, where we found the mathematics in the soil. Down somewhere we found like the leg bones, the flutes made out of the leg bones, and those musical instruments. How does that relate to how mathematics?
Yes.
Does it relate to mathematics?
Well,
And if so,
that's
how?
another good question. We could create a flute, ocarina, or a lute and play in an agreeable scale, mode, tot, rag, or whatever, without any mathematics. You just move, like sitars have movable frets. You move them around until you like the sound. But what happens when people disagree and they want to play together polyphonic music? They have to tune two different instruments similarly. That's where the mathematics comes in. Even if it's just a question of measuring the distance between holes of frets and reproducing that distance one machine and another. The thing is that if the bore of the flute is different, so I showed two flutes. One was made from the leg bone of a red-crowned crane, and the other was made from the leg bone of a griffin vulture. These bones, and in fact even two bones of the same bird, might have different diameters, in which case you'd have to have different spacing between the holes, and therefore you would have to have recourse to the shaman or the mathematician of your tribe in order to scale up. You see, you'd have to do a little bit of arithmetic to actually get the different instruments in tune. So musical arithmetic became this huge, complicated field. It's very difficult if you read any of the great books on these different tunings, micro tunings, and so on. It's very difficult. So what I'm suggesting, and I cannot prove, is that Paleolithic people had advanced very far in their sophistication of musical arithmetic. You can have the music without the arithmetic, but you have the music and the musical arithmetic. You can then make better music, which is polyphonic, which involves everybody in the tribe playing together in the cave, dancing, and of course, taking psychedelics.
I have a question about the music of the spheres. When that music is created, are there boundaries to that music which are subjective? Like, does that sound depend on what size of ethereal being you are? Is it you start one place and the next tone is relative to the other planets? Is that a subjective scale for those planets, or what anchors it?
Well, yes. It's the music of the spheres that I played has been rescaled to fit in the auditory range of a normal human. You see, so there happened to be, according to Kepler's rules having to do with the angular velocity of the planet seen from the sun, one of the foci of its elliptical orbits. According to that rule, it gives only relative tones that have to span a range of 7 octaves, which is about what we can hear. So if Kepler were writing for a dog's ear, then he would pitch them a bit higher, but there would still be 7 octaves difference there. So if you think of the differences, there's something absolute about it. And 1 octave, see, people agree. What is an octave is a recognizable interval. Everybody agrees that no matter where the tonic, the bass note is. You see, so on the relative scale, like octaves, like musical notes, and so on, Kepler's music of the spheres is not subjective. It's only retuned for a given ear, like when you transpose from the key of C to the key of B flat on a trumpet, for example.
Well, I think we can continue the discussion after the talk for the goodies. Feel free to grab Ralph and ask him your question or tell him what you think. And join me now in thanking him again for a stimulating lecture.
Thank you. Thanks so much for this great opportunity.